Welcome to this explainer. Today we're diving straight into something that is quite literally life or death, the procedures for working safely on or near energized electrical equipment. Let's get right into it, because when it comes to live electrical work, the margin for error is absolutely zero. We're talking about hazards that can change a life in a fraction of a second. So really, understanding these guidelines isn't just about ticking compliance boxes. It is literally about survival.
Now we have to start with the stark reality of the hazard we're up against, and that is arc faults. This isn't just a simple spark, right? It's an unintended and completely uncontrolled discharge of electrical energy straight through the air. This absolute nightmare scenario is typically the result of a malfunction, maybe some contaminant buildup or an insulation breakdown, and the result? It produces incredibly dangerous heat, plasma, blinding light, and just deafening sound.
So to navigate these extreme dangers, we're going to break this survival guide down into 6 key parts. First, the danger of energized work. Second, when live work is actually allowed. Third, assessing and controlling risks. Fourth, safe work method statements. Fifth, the role of safety observers. And finally, tools, PPE, and safer design.
All right, let's jump right into part 1, the danger of energized work.
What is truly terrifying about an arc flash is the sheer scale of the incident energy. To put this into perspective, the plasma gas generated can actually reach temperatures hotter than the surface of the sun. I mean, that's just wild. This massive release can cause serious burns to anyone nearby. In fact, the established arc flash boundary is the exact distance where a person would be exposed to a curable second-degree burn, which they measure at 1.2 calories per square centimeter. Oh, and it could also instantly ignite flammable materials, including your own clothes, and completely trash expensive plant and equipment. The main takeaway here? Your risk skyrockets the closer you get to those energized parts.
Moving on to Section 2. When is live work actually allowed?
Well, the rules are incredibly strict here. Live work is only allowed if life-saving equipment absolutely has to keep running or for essential testing to figure out if a circuit is energized, or if there is literally no reasonable alternative, like avoiding widespread outages to critical infrastructure. But here's the kicker. It is absolutely, categorically never allowed to bypass isolation just because turning the power off is inconvenient or takes a bit more time. You never, ever work live just to save a few minutes. It's just not worth it.
Which brings us to Section 3, assessing and controlling the risks.
This whole strategy relies heavily on what's known as the hierarchy of control. As you can see, we must always prioritize the most reliable controls at the top, meaning eliminating the hazard entirely, long before we even think about relying on personal protective equipment, or PPE, way down at the bottom. Think of PPE as your absolute last resort, not your initial game plan.
So, turning this into actionable steps means systematically working your way through these controls. Step 1 is eliminate. Can we de-energize or maybe use a plug-in test instrument to do RCD testing remotely? Step 2 is substitute. Could we replace a standard switchboard with an arc-resistant one? Step 3 is isolate, utilizing techniques like remote switching to keep people out of harm's way. Step 4 is engineer, installing physical barriers. Step 5 is administrate, putting strict rules in place to limit access to the area. And finally, Step 6 is PPE, using arc-rated clothing, which, I'll say it again, is your absolute last line of defense.
All right, on to Section 4, your Safe Work Method Statement.
Now, your Safe Work Method Statement, or SWMS, is not just some piece of paperwork you fill out and stuff in a drawer. It's a highly accessible action plan. It has to specifically identify the electrical work you're doing. It needs to lay out the exact hazards and the risks associated with them. You also have to clearly describe the measures you're going to take to control those risks and detail exactly how those controls will be implemented, monitored, and reviewed on site. Plus, you've got to include that prepared risk assessment we just talked about. Everybody on site needs to understand this document inside and out.
And as you're putting this plan together, keep this critical safety mantra in the back of your mind. All materials should be regarded as conductive unless proven otherwise. This is a huge reminder that you don't actually need direct contact with a copper wire to get hurt. Even gases and liquids can provide a current path for a deadly shock or fault. Basically, assume it conducts until you prove beyond a shadow of a doubt that it doesn't.
Let's move into Section 5, the role of safety observers.
So, for high-risk tasks, having a competent safety observer is absolutely mandatory.
We're talking about things like fault finding at a switchboard with a high prospective fault current, or installing and replacing components, or connecting final subcircuits in an energized board with an incident energy of more than 4 calories per square centimeter. In these specific situations, your observer has to be completely competent to perform rescue and resuscitation. And this is crucial. They cannot be distracted by other tasks. They need the ultimate authority to just yell stop and halt work immediately if the risks get too high.
But this actually brings up an interesting question that we hear all the time in the field. When can you skip a safety observer? Is there ever a scenario where you don't need someone watching over your shoulder during energized work?
Well, the answer is incredibly narrow. The one and only legal exception is if the work consists purely of testing, say checking the polarity of an installed outlet, and a formal risk assessment confirms there is absolutely zero serious risk involved. If both of those specific conditions are not perfectly met, no exceptions, you must have an observer.
Finally, let's wrap up with Section 6, Tools, PPE, and Safer Design.
When you're relying on that bottom tier of the hierarchy of control, your gear basically has to be flawless. You've got to use Category 4 rated test instruments for mains voltage equipment so they can withstand massive impulse voltages. For your clothing, any thermal outer garments have to be flame retardant. And please, listen to this next point. There can be absolutely no flammable melting synthetic layers in your clothing. If an arc flash hits, melting synthetics will cause catastrophic permanent injury, literally melting right into your skin. And lastly, just make sure all your tools are properly tested, maintained, and completely fit for the job.
But beyond our personal gear, we're also protected by smarter, safer equipment design. This includes the physical segregation of switchgear using barriers. We're also seeing some amazing tech like optical arc fault detection devices that literally spot the early light flashes of an arc. When you pair those with arc quenching devices, they can extinguish arcs in mere milliseconds by applying a rapid short circuit, which basically kills the arc before it can even expand. You can also optimize protection settings on your breakers to dramatically drop the incident energy before disaster even has the chance to happen.
So as we wrap up this explainer and you head out to your next job, I want you to ask yourself one vital question. Are you treating every single conductor as energized? Remember the absolute golden rule of electrical safety. Always test before touching. Because when you're dealing with live electrical work, complacency is the ultimate invisible hazard. So what steps will you take today to ensure that you and your entire team make it home safely?